don't we get started? So, are there any questions from yesterday? I'm going to review some of the things that I said at the end last time. So the plan is it's a lot of material to get through, but I want to review the things that I said yesterday. Just talk again about the definition of the Heegaard Floer complexes. Maybe do an example or two or three, and then dive into not Floer homology and take it from there. And then we're going to see some things about L spaces. So, okay, great. So let's just remember how we did this. Remember we said, so we looked at a Heegaard diagram, which is a surface and some alpha circles, beta circles, and a base point. And the base point is going to be important for defining the complexes. Okay, so then we looked at sort of T alpha and T beta contained in the symmetric product. Okay, so let's the most basic example we did was of the Heegaard diagram for S3. Okay, so now let's try to draw a slightly different Heegaard diagram for S3. Okay, so it's almost the same Heegaard diagram, except that I've isotoped the blue curve somewhat. So this is, again, alphas are red, betas are blue. I'll continue to keep the base points where it was before. So now I have a different Heegaard diagram, and now you see that I have three intersection points. Okay, so I should be getting a different chain complex. So maybe I'll call those three intersection points A, B, and C. Now, remember what we said in the differential. So in the genus 1 case, things are really easy. Okay, in the genus 1 case, we're really just looking for maps of a disk into the surface, right? So let's just remember what the differential said. So CF hat was generated by over Z. Actually, I'm going to be really lazy for the rest of this seminar and do everything with coefficients in Z mod 2. So henceforth, we're going to work over the field F, which is going to be Z mod 2Z. Okay, and actually, it's not really just being lazy. Some of the results that we're going to get to later on, basically anything that uses bordered, is going to be is only going to make sense over Z mod 2. So so whenever I say L space, I'm going to mean L space with coefficients in Z mod 2, etc. And I think that will be the convention for some of the other talks if we're bringing in various of these results. Okay, so anyway, CF hat is going to be generated over this ground field by all the points by all of the well, I guess I can just say T alpha intersect T beta. Okay, and so here we have three such things. Okay, and the differential and then I could also sum over, so I'm going to sum over all of the homotopy classes of disks that connect X and Y, which have the property that their Maslov index is 1, and then the second thing that I need is that their multiplicity at the base point should be 0, okay, now I'm going to count points in this moduli space. So, okay, and then there we go. Okay, and so now, and that's going to be my first count. Okay, so one thing that I should say that if this moduli space is non-zero, one of the first important facts is that whenever this moduli space is non-empty, as long as there are any holomorphic representatives, that immediately tells me that all of the multiplicities of the domain of this disk must be non-negative. Okay, and somehow this is the statement of this is that if you have two complex subvarieties of almost complex manifold, then they intersect positively at every point, right? So when we talk about the symmetric product, right, we have this codimension 2 subvariety, which is given by the base point, and then we have some holomorphic curve, and that holomorphic curve, so therefore they must have only positive intersections. Okay, so that of course puts a lot of restrictions on where we can find some disks. So where are the disks here? Well, here's one. Okay, so remember what we were supposed to look for. We were supposed to look at a holomorphic map of the unit disk in the complex plane, taking I to the source generator minus I to the target generator. That's the x and the y here. And then it's supposed to be, when you tilt your head, it's supposed to be alpha on the left and beta on the right. That was the convention that I spelled out. So this region here would count as a disk from A to B. Okay? And then similarly, this region here would count as a disk from C to B. Okay, so this is telling me that the differential, and that's all. That's all we can find here. So that the differential of A here is equal to B, and the differential of C is equal to B. So we can graphically represent this that way. Okay, so where now the height has somehow become the grading, and lo and behold, we see that the homology is rank 1. Okay, so the homology is generated by, A minus C. And you can do this with signs also, but I just don't want to tell you how to do that. Okay, so that would be sort of the first example here. Okay, now let's just notice what would happen if I changed the base point, right? If instead of taking the base point here, I had taken the base point to be here, okay? I have changed the chain complex, right? And how have I changed the chain complex? Well, now suddenly this differential from A to B has gone away, and there's just a differential from C to B. But what's remarkable is that the homology hasn't changed, okay? So, all right, so maybe I should actually state a theorem eventually, because I kind of didn't do that yesterday. But before I do that, let me actually tell you about a little bit more about the role of the base point. So the theorem, so the full versions of the complex, the base point starts coming into play for the other versions. Okay, so let's let CF infinity of the Heegaard diagram. Well, okay, maybe you should say, so CF infinity is going to be generated by all, so it's going to be generated over the field again by now base points, or sorry, all of the intersection points together with an integer. Okay, so this is, for some reason, the tradition of how we write these is x comma I. And the rule that we're going to take is that this is now going to become a module over f adjoin u, and the u action is going to is just going to decrease the I power, the I variable. Okay, and now the differential is going to count, it's going to be the sum over all again. Okay, so we're going to take the same kind of sum. Again, we need the Maslov index of phi to be equal to 1. That means the moduli space will be rigid, and then now the way we incorporate the base point is by putting it into the I factor. Okay, right. So now this is going to be the full version of the complex. Now here's the point. What as we said is that for any term that is appearing with non-zero coefficient here, meaning that they're holomorphic representatives, nz is positive, or is non-negative. Okay, so this is greater than or equal to 0. And what that means, so this is what we call CF infinity. Now, CF minus is therefore going to be the subcomplex generated by all xi with I less than 0. That's why it's called minus, okay? And it's a subcomplex for exactly that reason. Okay, and then CF plus is going to be the quotient complex. Okay, so those are the different versions. So as a result, we get exact sequence. So so let's just think about what these we get as exact sequences. Well, there's right. That's just coming from. So this is just inclusion and projection. And so a short exact sequence of complexes turns into a long exact sequence of homology groups, right? So those are going to be that's going to be on homology. Okay, now what about HF hat? How can we think about HF hat or CF hat? Well, here's what we can do. Let's just think about the plus version of the theory here. Okay, so that's going to be sort of generated by all terms with I greater than or equal to 0, with the proviso that when we have disks that sort of take us into the I negative range, we're modding out by those. Okay, so therefore we can think about CF hat as being the I equals 0 version. Okay, so that is to say, we only look at it's the subcomplex of plus that is only the things with I equal to 0. And so we can say it nicely this way, that CF hat is the kernel of the U map on CF plus. Right? And as a result, we see that if so that means we get another exact sequence. So so there's this exact sequence from HF hat to HF plus to right. So now we have these exact sequences. Okay, very good. Now, what can we say about these? Let's, now the other thing that we said is that each of these groups comes with a decomposition by spin C structures. Okay, so each version by spin C structures, and I spelled this out last time a little bit. I guess I didn't tell you what a spin C structure is. I'm still not going to tell you what a spin C structure is because it's kind of abstract. But the point is that there's the basic idea is that when I have two generators, well, let's actually look at an example of this. Okay, so I'm going to draw another Heegaard diagram now. This is going to be a Heegaard diagram for a lens space. So okay, so this is L31, I think. Depending, right? Cameron mentioned lens spaces in his talk yesterday. Okay, so now again I see these generators A, B, and C. Okay, and now my claim is that I can never find, or if I were to have a disk, let's say, from A to B, then its boundary, right, what would its boundary be? We call this epsilon, right? It's a path that goes from A to B along a red curve, and then from B back to A along a blue curve, okay? And what I claim is I can never find such a path that is null homologous in the homology of the surface, even by adding on multiples of like the complete alpha or the complete beta circles. I can never find such a path. So there are no disks from A to B, okay, and therefore those are in different summands of the group, okay. So that's going to be my spin C decomposition, right? And there are 3 of them, right? And we see that there are 3 spin C structures because H lower 1 is of order 3, and there are 3 generators, okay. And in general, what we saw is that the rank of HF hat. So let's maybe say this carefully. So now actually let me specify to some things that are true when Y is a rational homology sphere. Oh, actually, first, why don't I just state a theorem? So just to be. So this is just try to encapsulate some things all at once. So first thing is that d squared is equal to 0 all the time, okay? And the second thing is that CF infinity, CF plus, CF minus, CF hat of, so, or maybe let's say it, for any Y and spin C structure, so for 3-manifold Y and spin C structure S, the complexes CF hat of Y spin CS, CF infinity of Y spin CS, CF plus, CF minus, etc., are invariant up to chain homotopy equivalence. Okay, so that is to say that their homologies are therefore invariants of the 3-manifold with the spin C structure, and they're HF hat, HF infinity, HF minus, HF plus are invariants. Okay, now there is some subtlety in this statement. In the original way that it was proven, it was technically proven that their isomorphism types were invariants. Thanks to work of Anders Juhas and Dylan Thurston, we know that really as groups they are invariant. There's some subtleties of naturality that one has to think about, and one could talk about that for a long time, so I won't. But yes, so that's the statement of this theorem. And you have to pay a little bit more attention to when you're dealing with manifolds that are not rational homology spheres. There's some subtlety, as I said, about what kind of Heegaard diagrams you're allowed to use, which we will sort of avoid. So, okay, great. So now let me specialize a little bit to the case of rational homology spheres, since those are sort of what we're mostly interested in. Okay, so when Y is a rational homology sphere, okay, one of the things that we saw is that the total rank of HF hat of Y has to be greater than or equal to, well, we said it was the Euler characteristic of HF hat of Y, which was equal to the Euler characteristic of CF hat of a Heegaard diagram, right? Which was just equal to the determinant of Y. So where the determinant is equal to the order of H2, order of H1. Sorry. Okay, so that was the first thing that we saw. Okay, and in fact, this turns out to be true on a spin C structure by spin C structure level. So in fact, the rank of HF hat of Y in each spin C structure has to be at least 1 and has to be odd because the Euler characteristic is 1. Okay. Now we said that Y was an L space if this was actually if we had equalities here. Okay, so lens spaces are going to be an example. So Y is an L space if the rank of is equal to the determinant of Y. Okay, now examples being lens spaces. We'll try to come up with some more by the end of this lecture. What are some ways? So let's just. So since we talked in some detail about the complexes, it seems natural to take a little digression and introduce a nice family. So what was the nice property of these lens space diagrams, right? And this was L31. I saw exactly one generator sitting in each spin-C structure, right? And therefore, automatically, there could be no disks, right? Because you can't, if I have a chain complex, I can't have a differential from X to itself, right? Because then D squared couldn't possibly be equal to 0. So automatically, when I just saw exactly the number of generators, right, by this other characteristic argument, there can't be any differential. Okay, so let's define a strong Heegaard diagram for a rational homology sphere. Y is one for which the number of intersection points is exactly equal to the determinant. Okay, and we're going to and so immediately, so if Y has a strong diagram, Y is we call it a strong L space. Okay, so automatically, so this is the idea of like being an L space on a chain on the chain level. Okay, now I have no idea what manifolds these are, right? Because how might one find a strong L space diagram? Well, maybe you have some manifold. It does, and it has like a nice simple Heegaard diagram of low genus, but it's not a strong diagram. But maybe it also has a strong diagram of genus 1,000,000, right? So this is not like an easy property that that we know how to test for. So this is an interesting, in light of what Cameron was telling us yesterday, thought I'd mention this theorem, which is, so this is a theorem of myself and Sam Llewellyn. If Y is a strong L space, then pi1 of Y is not left orientable. Okay, now that's really weird. What should these things have to do with each other? Well, remember last time I said that a Heegaard diagram gives you a presentation for pi1 of the 3 manifold, right? You look at the generators correspond to the alpha circles, and the relators correspond to the beta circles, and you can look at the and you read off the relations by sort of counting intersection points. Okay, so it turns out, I'm not going to go through this argument, but it turns out that you can actually recover the non-left orderability directly from that presentation. So this is maybe some slight bit of evidence for that conjecture. Anyway, that's just slightly tangential, but I think it's a nice. I was happy to see this happen. So okay, let's get back to any questions about anything.
You conjectured strong L spaces are like double branch covers of quasi.
Yeah. Okay. So here's the fact. So if K in S3 is an alternating knot. So not quasi-alternating. So is an alternating knot. Maybe I should mention this. And sigma of K, which is the branch double cover, is a strong lens space. So this is a result of Josh Green, who basically writes down a very nice Heegaard diagram for the branch double cover of an alternating knot, or the branch double cover of any knot, and when that knot happens to be alternating, that diagram turns out to be strong. Okay? Conceivably, these could account for all of the strong lens spaces. I don't know why that would be true.
You probably have to say link.
Link, yeah, that's right. I should say link. Conceivably, every strong null space could be achieved in this fashion. I mean, there's no good reason for that. We just don't know any other examples. So of course that's still a pretty restrictive class of math. But it's some connection. So okay. So let's now let me give a nice little. So let me state one fact and then give a nice little exercise. So here's going to be the theorem. So for again, for Y a rational homology 3-sphere, in each spin C structure, HF infinity is boring. So HF infinity is sort of always the same. It's just going to be isomorphic to a single copy of the ring of Laurent polynomials in one variable, right? So you can see that, for instance, for the lens spaces, and just because for the L spaces, right, or for S3, for instance, right, there was just one generator, and now we take this complete tower of generators, okay? And as a consequence of this, what we see is that HF minus HF minus is going to be just a copy of the ring of polynomials plus some finitely generated abelian group. Okay, so, and HF plus is going to be, well, sort of everything that's left from here. Okay, so usually maybe by tradition we like to think about 1 as living in HF plus rather than in HF minus, right? These are the same. Plus, again, some finitely generated part. And in fact, these two pieces are isomorphic. Okay? So now, let's sort of give a little exercise. Right, the way that we see these is this is going to be all using these exact sequences that I laid out before. Okay, so now a little exercise is that if HF hat of YS is just of rank 1, then HF plus of YS is isomorphic just to okay, so that's going to be the fact about about L spaces, right? So when you have an L space, HF hat is sort of as simple as can be, right? And what that immediately tells you is that HF plus is also as simple as can be. Okay, and so the sort of moral of the story is that when you're dealing with L spaces, there are a lot of things where sort of you don't need HF plus because it's just it's kind of all of the information is contained in HF hat. Okay, but it's not true in general that like as soon as you know HF hat, you know HF plus. There's just more structure in the plus theory than in the hat theory, but in L spaces, that sort of all of that goes away. That's one of the reasons that we find this class of spaces to be so interesting. So, because we can work with them, right? The other, I guess, I haven't been talking much about the computational aspect, or like, you know, the holomorphic curve counting, but it's not fun, right? It's in general difficult. Now, in principle, well, now in principle, sort of they can all of the versions can be done algorithmically in one way or another. HF hat from Heegaard diagrams can be done algorithmically. And the idea is that there's a notion of a nice diagram. I don't want to go too far down to this rabbit hole, but there is a certain class of nice Heegaard diagrams for which HF hat can be determined completely combinatorially. Okay? Basically, you push all of you make sort of everything about the Heegaard diagram nice, except maybe the region where the base point is contained. And since we don't care about since for the purposes of HF hat, we don't count any disks that go over the base point, if we sort of push all of that badness into the region that we don't like, and then we basically argue that the rest of the holomorphic curve counting is completely combinatorial, as long as it's away from the base point, that's the whole idea of Charkar and Wang. We'll see another idea. We'll see another way in which hat, you know, we can do stuff with hat that we can't do with the others. But for L spaces, you know, all of that works out great. So, okay. Any questions? I know I'm saying a lot, and many of you have probably seen many of these things, but it's just good to be on the same page. Any questions? No? Okay. It's early. Great. So now I want to talk about not Floer homology, cannot Floer homology. Okay, and this is due sort of simultaneously to Odervos and Szabo and Dick Rasmussen. Okay. So the idea is going to be, we want to study not just a three manifolds, but perhaps a three manifold with a knot in it. And how are we going to obtain such a thing? So the first observation is that, so given a doubly pointed Heegaard diagram, so a Heegaard diagram with two base points, W and Z, you know, which are not on the curves, we're going to obtain a knot. Okay, and how are we going to do that? Well, let's just think about our sort of Morse theoretic picture of the Heegaard diagram. Okay, so remember we had our alpha circles, which corresponded to like the ascending submanifolds of the index 1 critical points. And then we had the beta circles, which corresponded to the descending manifolds of the index 2 critical points. Okay, and so therefore any point that wasn't on either an alpha circle or a beta circle, if you flow it up with the Morse function, you get to the top, to the index 3, and if you flow down, you get to the bottom. Okay, so if I have a point that corresponds to a flow line like that, okay, well, if I have 2 points, 2 such points, I get 2 flow lines. And 2 flow lines connecting to the same 2 points, that's a knot. Okay? And my claim now, and any knot can be obtained in this fashion. So, here's another way to articulate this. Okay, so what we're going to do is connect Z to W with an arc in sigma minus the alpha circles, right? So the alpha circles were a linearly independent collection of G curves on a genus G surface, and therefore they are non-separating. So I can always connect these 2 points in an essentially unique way, right? Because, well, no, right, no, not an essentially unique way, but when I cut along this surface, I guess it has some pi 1, but it's, but right, so I can make that connection, and then I can connect W to Z with an arc in sigma minus the beta circles. Maybe I'll call this arc T alpha and this arc T beta. Okay, so let's see if I could sort of try to do that. Well, I guess I've kind of easy here, but if I connect from one point to the other point, maybe I'll call this Z and W, right? I can push this arc. Then what I'll do is I will push T sub alpha into the alpha handle body, and T beta into the beta handle body. And that's going to be another way of giving a knot. And in fact, if I tell you which point is Z and which point is W, then I have an oriented knot. And different papers have different conventions about which way the orientation of the knot is supposed to go. I think this is the right one, but that's based on a coin flip. So, well, of course, what do we mean by right convention? But I think, okay, so now, how are we going to get some information out of this? Okay, so here's going to be the first observation. So if Y is a rational homology sphere, so, or more generally, if you think about this knot as being an element of H1 of the three manifolds, as long as that's a torsion element, then for any two generators, X and Y, so here's what I'm going to say: the quantity NZ of phi, and if I take any disk connecting two generators, then this quantity, the quantity NZ of phi minus NW of phi, is independent of phi. Okay, so in the rational homology sphere case, any two disks are related by just adding a multiple of the entire Heegaard surface. Okay, those are somehow going to be the only two, the only just that's a matter of linear algebra in some sense. In the more general case, you have to think about what we call periodic domains, and I've been deliberately vague about that. But right, if I add just a multiple of the whole Heegaard surface, I change NZ and NW by the same amount. Okay, so this quantity is independent, and what this is going to turn into is what an actual grading. So let's just for simplicity at the moment, assume that K is actually null homologous. Okay, so we have to be a little bit more careful if it represents like a torsion class of higher order, but we're going to assume that K is actually representing 0 in H1 of the three manifold. And mostly we're going to do this with three manifold being S3. So this is clear. Okay, so then what we can do is we get a quantity called the Alexander grading. Okay, and it's going to be a function on the set of generators. Maybe we'll call it A from T alpha intersect T beta to Z, which is characterized up to an overall grading shift. Up to an overall shift, this function is characterized by A of x, so for x and y in this set, A of x minus A of y is equal to nz of phi minus nw of phi. Okay? So that's going to be what we call this Alexander grading. Now, we'll tell you how to pin down the shift. At some, we'll see that in a moment. Okay, but that's what this function is going to be. Okay, so.
Make it a bit more concretely as an evaluation of C1 on the class represented by the capped off surface.
Yes, that's right. So really, what as BG said is this is a species. So I can tell you an explicit formula for writing this function down, which actually is a very useful thing to know. But what that explicit formula has to do with is a generator is supposed to give rise to a relative spin-C structure. And a relative spin-C structure, it can be has a first-order class, which is a relative homology class. It's a class in like Y relative. Excuse me. It's a class homology H2 of Y relative to the knot, and you can evaluate that on the homology class of a Seifert surface and spit out a number, and that's what this Alexander grading is measuring. And there's actually just an explicit diagrammatic formula for this, which we could talk about at another time. Okay, so let's just see an example of this. Let's suppose I take this Heegaard diagram, again for S3, and I take this to be my Z and this to be my W. Okay, and I have, so now I'm going to call my generators A, B, and C again. Okay, so the first exercise is that this Heegaard diagram presents the right-handed trefoil. So this okay, this is going to be a nice little exercise in drawing Heegaard diagrams and thinking about the recipe that I spelled out here. Okay, so now let's see if we can figure out what the Alexander gradings of the generators are. Well, let's see. A of B minus A of A is equal to, so there's a disk from B to A here, right? So that disk hits Z once and W 0 times, so this is equal to 1. And then similarly, there's a disk from B to C. A of B minus A of C is equal to, so there's 1 minus 0, this is 0 minus 1. So as a result, that means that B has Alexander grading 1 greater than A, and C has Alexander grading 1 greater than B. Okay? And we can pin that down, so we're going to say, the way we'll ultimately pin this down is we'll get it to be sort of symmetrical. So we're going to say that A of A is equal to minus 1, A of B is equal to 0, and A of C is equal to 1. Okay, that's going to be our grading. Now, what does this mean in terms of chain complexes? Okay, now we're going to do something a little unusual here, which is that previously we were calling the base point was going to be Z, was what we were calling the base point Z. Now I want to treat sort of W as the base point, although actually this is a somewhat, we're going to see that what Heegaard Floer homology is really all about is sort of understanding the relationship between the two base points. But I want to treat W as sort of the base point. Okay, so let's think about CF of sigma alpha beta W, and let's just do CF hat. Okay, so remember that was a chain complex with A, B, and C as its generators. Okay, and so there were. I'm going to draw it this way. Okay, so the horizontal position here is meant to represent the Alexander grading, right? And the vertical position, I guess I didn't tell you about the Maslov grade, or the homological grading. I guess we talked about the Z mod 2 grading. So it turns out for rational homology spheres, that grading could be lifted to a relative Z grading on any spin C structure. Okay, and so let me maybe just state this formula. Okay, so there's going to be this separate grading formula, which is going to come from the this is the homological grading. So I'm going to gloss over that for the moment. If you've seen it, great. If not, don't worry about it. Okay, so now let's just see what happens. So remember, we're not going to allow a disk from B to C here because there's a base point, but we do allow a disk from B to A. Okay, so now what we notice is that this Alexander grading gives us a filtration. So okay, so what we see is that if Y occurs in the boundary of X in CF hat, then what does that mean? That means there's a disk in CF hat of, again, sigma alpha beta W. What that means is that there's a disk from X to Y that avoids W, and maybe it hits Z and maybe it doesn't. Okay, but then A of X minus A of Y is equal to NZ of phi, which is greater than or equal to 0, because NW is 0, right? Okay, and so immediately that tells you that this is a filtration. So CF hat of Y, so CF hat of this 3 manifold represented from this Heegaard diagram acquires a filtration. Okay. Namely, the different filtration levels are given by F sub I is generated by all X with the Alexander grading of X less than or equal to I. Okay, and each of those becomes a subcomplex. Okay, and now the theorem well, I'm going to say this in weak form, is that the filtered chain homotopy type of this filtration, of this filtered complex, is a not invariant. The filtered chain homotopy type is a not invariant. Okay? So it's more than just, what does that mean? That means that if I have any two doubly pointed Heegaard diagrams presenting the same knot, I can find a chain map from one to the other, which is a chain homotopy equivalence, and it's a filtered map, so it takes the ith filtration level of one into the ith filtration level of the other. Okay? Now, that's a sort of rather abstract concept. How can we maybe work with something a little bit more concrete? Well, one way we can do that is we can take the associated graded complex. Whenever I have a filtration, whenever I have a filtered complex, I can, so the associated graded complex that means look at, that is to say, take the ith filtration level and mod out by the I minus 1th filtration level. And that is to say, we're going to look only at the portions of the differential that preserve filtration level, which is to say, look at only the disks which miss Z. Okay, so CFK hat of sigma alpha beta WZ is going to be, again, it's going to be generated by, well, this points in T alpha intersect T beta, and we're going to say that the differential is going to be equal to the sum, again, and summing over all y, summing over phi, where mu of phi is equal to 1, and now we're going to require that nw of phi and nz of phi are both equal to 0. Okay, and then same deal. Okay, that's going to be the sort of most basic version of not Floer homology. Okay, this is called, so the homology of CFK is called not Floer homology. And that's what we call HFK hat of YK. Not Floer homology, because for some reason we all read from right to left. Okay. So great. So what is this? This is a bigraded not invariant. Okay. It's so. Maybe let me just state stuff. State some properties of this. So I'm going to, just to simplify, well, I guess I don't really need to. I've been saying that K is a null homologous knot. Okay, so just if we let's just to simplify, let's say Y is a homology sphere. And usually I'm going to mean S3, but all of this makes perfect sense otherwise. Okay, so that means that we have this invariant. So HFK hat, and then K is contained in Y. Okay, so what are the things that I can say about HFK hat of YK? Well, the first statement is that it has a bigrading. Okay, and the statement of the bigrading is that traditionally we write it this way. So this is the Alexander grading. Okay, and then this, the M, is going to be the Maslow for homological grading. Okay. Yes. Yeah. So so I haven't gone into the details, but yes, this can be pinned down. Both of these can be pinned down as absolute integers. Okay. And I sort of have glossed over how that's done. So what are the basic properties of this group? Okay. So first of all, what I can do is I can take an Euler characteristic, and just as we saw with HF hat, that the Euler characteristic of HF hat was some number, right, and that number was something topological about the 3 manifold, namely the order of H1. It's going to turn out that the Euler characteristic of so I'm going to take the Euler characteristic with respect to one grading, namely the homological. And I'm going to keep track of the Alexander grading sort of separately. So let's just take the following sum. So we're going to take minus 1 to the m, and then just take some variable t to keep track of the Euler characteristics and count okay, so this is what we'll think of as a sort of graded Euler characteristic. Okay, it's within each Alexander grading, I'm taking the Euler characteristic with respect to the Maslov, and lo and behold, this is actually equal to the Alexander polynomial of the knot. Okay, there are a lot of ways to see this. I think Ellie Grigsby's paper about this is probably the best explanation that I have read, relating this to Reidemeister torsion, which is a way of thinking about the Alexander polynomial. So the original way that Ojibwa and Sabo talked about this was in terms of the Skane relation, but I think, so a much like you can understand all of this on the Heegaard diagram level, which I think is a really nice way of thinking about this. Okay, so that's one basic fact, right? Now this should somehow tell us some things about the knot, right? So I just finished teaching an undergraduate seminar on knot theory this semester, in which we learned. Well, the students were doing the lecturing, so how much actual learning got done is an open question. But one of we spent some time looking at sort of the basic properties of the Alexander polynomial. One of those basic properties is you compute it from a Seifert surface, right? And therefore you get this nice bound on the Alexander polynomial. The breadth of the coefficients in the Alexander polynomial gives you a lower bound on the genus of a knot, right? Okay, so one might perhaps expect to see a similar statement about this knot Floer homology, and not only do you see such you not only see a lower bound, but it turns out that the maximum of A of all Alexander gradings for which HFK hat of YK in that Alexander grading, summed over all homological gradings, is a non-zero group, is actually equal to the knot genus. So knot Floer homology detects the genus. So this is a fact of Sabo. Okay, that's amazing. That means in particular that it detects the unknot. You can immediately tell, right? Oh, and there's a symmetry. So what I didn't say is that, so this is also equal to minus the minimum of A for which blah, 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 blah. Right, so the Alexander grading is the knot Floer homology is supported in Alexander gradings ranging from minus the genus to the genus. That's a way of saying this. Okay, so that's one of the nice basic facts. Okay, right. Actually, let's just look at that example of the trefoil that I just erased. So for the trefoil, okay, I drew those. So this is going to be generally speaking, the way we draw this is we put the Alexander grading on the x-axis and the Maslov on the y, and those were my three generators, right, that I wrote down before, right? So I had 1 in Alexander grading minus 1, 1 in 0, and 1 in 1. And the Maslov gradings, I claim, were as I've drawn them. So minus 2, minus 1, 0, minus 1, 1. Okay, so there we go. If I take the graded Euler characteristic, what do I see? I see t minus 1 plus t inverse, which is good, because that's the Alexander polynomial of the trefoil. Okay, let's just mention another fact, and then maybe we can take a short break. Okay, so one more fact. Okay, well, let me, so this is, I guess, in one direction comes from Ojolas and Szabo, and then the more interesting direction comes from Ni and Gugini, is that K is fibered if and only if the Floer homology in that maximal group there, in the genus, in the Alexander grading equal to the genus, is actually rank 1. Okay, so so Ojolas and Szabo proved this, the forward implication, and then Ni and Gugini proved the reverse implication. So this is an amazing fact, right? So again, this is corresponding to some basic fact about the Alexander polynomial, which is that the Alexander polynomial of a fiber knot is monic. Okay, and now this is saying that the Heegaard Floer homology of a fiber knot is monic, and the converse holds as well. Okay, so that's those are some of the basic facts about knot Floer homology. Many of you have probably seen these before. Okay, let's just take, like, I don't know, a 1 minute break to stretch, and I could use a quick drink of water before we go on. But yeah, so why is the converse true? It relies on sutured Floer homology. Okay, so this top dimensional group can be identified with the sutured Floer homology of how do I say this? So you could take the complement of a Seifert surface, and the suture is just like the boundary. So this top dimensional group can be identified with that sutured Floer homology, and then you use sort of the disk decomposition theorem, and yeah, and some sutured stuff. It's amazing result.
Does a lot go into that fact that this is the same as sutured in that case, or no?
Yeah, I mean, it all uses the it uses a lot of this sort of sutured theory. I don't remember exactly.
You know, it's like a 40-page paper or something, so something has to.
Yeah. So, okay, so, very good. When I said a minute, I meant a minute. So let's keep on going with knot Floer homology. Okay. Oh, I know what I forgot to talk about. Okay. Okay, so what else can we do with this story? Let's see how we could perhaps use knot Floer homology to understand surgeries on a knot. Okay, so to do this, what we're going to have to do is introduce not only the hat version, but actually the full version of this story. Okay, so here's what we're going to do. So this is sometimes known as CFK infinity of YK. Okay, and it's going to be a chain complex again. So this is going to be generated by triples of a generator X two numbers now, okay? Except that they're not really independent of each other at all. What we're going to say is that we are just going to assume all the ways that j minus I is equal to the Alexander grading of that generator. Okay, this is going to be the sort of master complex associated to a given knob. Okay, the way we're going to think about this typically, let's work with our example that we've been, the trefoil example that we've been working with. What happened to that blue chalk? I thought it does. Great. So here we go. So once again, okay, let's see if I can do it correctly. Then I put, this was W and this was Z, correct? Good. Okay, so I'm going to think about this, this chain complex in the following way. The differential I want to put on here I'm going to sum over y, summing over phi, in the usual way, count the moduli space of phi. And now the two variables, I and j, are going to record the multiplicities of the disk at I and j. Okay? Now, of course, this is well defined because my condition was, right, that if when I have such a disk, I said that the Alexander grading of x minus the Alexander grading of y should be equal to nz minus nw, and so that's going to be consistent with this condition if you just check it carefully. Okay? So what's this going to look like? We're usually going to represent this on a plane where I and j are going to be, I is going to be the horizontal axis and j is going to be the vertical axis, and we're just going to draw the generators at those positions. Okay? So so we said that the Alexander grading of A was -1, 0, B is 0, C is 1, so I'm going to draw that as like A, B, C, A, B, C, A, B, C. Dot, dot, you know, continuing infinitely in both directions. Okay? And the differential, so let's see, let's look at the differential of this complex. There's a disk that goes from B to A that goes once over Z and 0 times over W. Okay? So those are going to correspond to the vertical differentials. Okay? And similarly, there's a disk from B to C that goes over W's. Okay? And there we go. That's going to be our chain complex. Okay? Now, I sort of alluded to this before. Right? I and j are not independent of each other. Okay? If I just kind of covered over this, if I just ignored this, the j's here, what would I have? What would I be describing? Be describing CFK infinity, or CF infinity of the 3 manifold with respect to the base point W. Okay, right? That's exactly what it is. I don't care. Like if I just forget about the J coordinates, that is to say, if I just look at, you just collapse this entire page on the, collapse the vertical axis here. Okay, I'm just describing the vertical complex of this. I'm just describing, the chain complex associated to the base point W. Now, if I instead decide to ignore the first coordinate and just think about the J's, okay, then I'm describing the Z complex. All right, I'm describing the chain complex of this 3 manifold with respect to Z rather than with respect to W. The interesting thing here is that by looking at those two things simultaneously in this fashion, I'm supposed to be extracting information about the knot. Okay, and indeed. It turns out that let's see how we can say this. So here's the theorem: is that the doubly filtered chain homotopy type of CFK infinity is a knot invariant. Okay, so one can obtain all sorts of information about the knot by looking at this doubly filtered chain homotopy type. Okay, now again, I mean, one thing you could do is just sort of take filtrations on that. If you doubly filtered chain homotopy types are a rather messy thing to work with. It would be nicer to have like isomorphism classes of groups. So we can take sort of the associated graded versions of this. What do I mean by doubly filtered here? I guess I should say the two filtrations are I and J. Okay, so the horizontal direction and the vertical direction. All of the arrows, another way to say this is if I think about this in this geometric fashion, all of the arrows point down and to the left, or down and or to the left. Okay, so that's right, and then the filtration, right? You could think of any if I take any region of the plane, which is what would be the right way to say this? Closed down and to the left. So like as long as you have a point, one point in the plane, then everything below and to the left of it is also in that region. Then that will describe a subcomplex. Okay, so we're going to use that type of information to do some things about the knot. Okay, and about so I can talk. So let me just sort of establish some notations. If I say something like C I less than 0, that's going to mean if I just say C with some conditions of I and J, I'm going to mean the corresponding subcomplex. So this is going to be the subcomplex of all points with I less than 0. Okay, and if I say C like I greater than or equal to 0, that's not a subcomplex, okay, but it's a quotient complex. So maybe I'll just call C is going to mean the whole thing. So or CFK infinity mod C I less than 0. All right, and so geometrically it's very easy to like picture these chain complexes. You just like erase the part. You only look at the part of that diagram that you might be interested in. Okay, so what are we going to do with any of these things? What I would like to do is describe a formula that is going to capture the surgeries, the Floer homology of surgeries on a knot. Okay, so let's just, I guess, as a quick reminder, just say a word or two about vein surgery. I'm guessing many people have seen this, but just to remind you, if I take, so okay, maybe, well, okay. I guess we can work with an arbitrary y here. Okay, so if I want to describe yn of k is going to mean y minus a neighborhood of k union a solid torus. So this is going to be Jane's surgery. So if I delete a neighborhood of k, I see now something with torus boundary, and I want to glue in a solid torus in a new fashion. So what's the fashion? How am I going to do that? Well, I just want to, in order to glue in a solid torus, I need to tell you where the meridian goes. That is, say, where does the boundary of a disk go? Right? I can accomplish the gluing in sort of 2 steps. First, glue in a disk, and then glue in the rest of the solid torus, which is just a ball. There's essentially a unique way to glue in a ball. So the only interesting bit of information here is where do we glue in the disk. So where we glue the disk to an n-framed longitude. Okay, and by n-framed, so this makes sense as long as as soon as I have a null homologous knot, okay, then there is a Seifert surface, and when I have a Seifert surface, I have a canonical framing on that Seifert surface, which is going to be the boundary of the Seifert surface. The boundary of the Seifert surface gives me a framing. Okay, it gives me a longitude, and then I'm going to call that 0, and then by adding copies of the meridian, I can parameterize the rest of the longitudes. So the n-framed longitude is going to be the one which is like the Seifert longitude plus n times the meridian. Okay, and so that gluing is going to describe y sub n of k. Okay, so let's just let's assume that y is a homology sphere, just to make our lives easy. And in most of the examples we're going to be talking about, it's going to be S3, but we might as well, just try to say things generally. Okay, so one fact to notice is that h1 of y sub n of k is equal to z mod n, is isomorphic to z mod n. Okay, therefore that is to say there are, if I'm interested in y sub n of k, there are n spin C structures on that manifold. So y sub n has n, y sub n of k has n spin C structures. Okay, now there's a good way of characterizing them. Okay, one way to do that is the following. So let's let w sub n of k be the two-handle cobordism. So that is to say, I'm going to take y cross I and attach a two-handle along k with framing n. Okay, so now if I have this Seifert surface here, so this is going to be, so S hat, so S is going to be a Seifert surface. For k, and I can cap it off to make a surface. So S hat is capped off in W, right? So I attach a copy of the handle. Now I have a surface. Its self-intersection number is n. Okay, and here's what I can do. So you do some basic So spin C structures on W, so on W sub n, those are going to be isomorphic to H2 of W, which is just Z. Okay, any spin C structure is, right, so this is a nice little Meyer-Vittorius computation if you, for graduate students. Okay, and so we can index these in a particular way. Let's do it as follows. S sub I is going to be characterized by the fact that I take its first Chern class. Okay, so let's see. The first Chern class of anything has the property that it is a characteristic covector, right, on in H upper 2, right? So a first Chern class evaluated on a homology class should be congruent mod 2 to the self-intersection of that homology class. Okay? So if I'm going to evaluate it on a capped-off cipher surface, that capped-off cipher surface, let's notice that the capped-off cipher surface has self-intersection n, okay? And so that's going to be the usual way of characterizing these things, okay? And it turns out that SI restricted to y sub n of k is equal to Sj restricted to y sub n of k if and only if I is congruent to j mod n. Okay, so this is going to be a way of indexing the spin C structures on the surgery manifold. Okay, so that's just so maybe I'll call that T sub I, math frac T, if you like. Okay, so that's just a little bit of notation to establish. Now, what I would like to describe for you is a formula that is going to give us the Floer homology of the n surgery in terms of the in terms of this doubly graded chain complex. In fact, I think I want to leave that one up here. Okay. And the place where we're going to begin, let's see if I can get this right. Okay, so here's what we're going to do. Let's define the following objects. AS plus, or maybe I'll call it AI. AS plus, okay, is going to be defined as the complex where so it's going to be the quotient of this chain of CFK infinity, where I mod out by a lower left-hand quadrant. Okay, and it's going to be the lower left-hand quadrant in which, so that is to say that either so this is going to be 3 quadrants, right? It's going to be everything to the right of 0 and greater than or and above s. Okay, and similarly, AS hat is going to be equal to, defined as a certain subcomplex of this okay, so let's just sort of, okay, so this is what a typical AS hat looks like. It looks like a hook, right? And AS plus is sort of everything above and to the right of that complex. Okay? So now, here's going to be a theorem. Okay. Okay. If So for all n sufficiently large, for s, let's say for integers s between minus n over 2 and n over 2, we have isomorphisms. AS hat is isomorphic to HF hat of the surgery on K in the spin C structure T sub S. And similarly, AS plus is isomorphic to.
Excuse me. Are capital N and little n different?
Did I?
Your inequality on S.
Oh, oops. Yep.
Thank you.
Okay. And similar statement applies about HF plus. Okay.
Actually, A homology of A.
Oh, yes, the homology.
Is N like the rank of HF rat of the surgery?
No, n is the
I mean, like, how do you get the sufficiently large N?
okay. So in fact, let's maybe actually state the answer. It's twice the genus minus 1. Okay. So there's an awful lot going on here. Why on earth should any of this be true? I could try to prove it, but basically what you do is you look at a Heegaard diagram for the surgery. You start with a Heegaard diagram for the knot, and then you use that to write down a Heegaard diagram for the surgery. And you, if you do the twisting enough, if the surgery coefficient is sufficiently large, you see that basically the only generators in a particular spin C structure are all supported in like a particular way, and then you identify the holomorphic disks that go into one complex with the holomorphic disks that go into the complex for the knot. Okay, that's all rather vague. I could spend some time on this, but I think it's more instructive to just do a bunch of examples of this and see what happens with, let's say, the trefoil and the two trefoils, in fact. Okay. So, any questions about this formulation here? Okay. And there's, by the way, there's a similar statement that one can make about large negative surgery. Okay. So for n less than or equal to 0, it turns out that basically you can make all the same statements, except that instead of maxes, I use mins here. Okay. So instead of looking at the hooks that are shaped like this, I look at the hooks that are shaped like that. Okay, and that's how we can make a statement about large negative surgery. Okay, so let's take that complex for the right-handed trefoil. Okay, which I've drawn over there. Now, here's a fact that should be familiar to many people. If I take +1 surgery on the right-handed trefoil, what do I get? Sigma 2 through 5 is the Poincare homology sphere. Okay, let's see if we can compute its Floer homology. So, what do I have to do? I should look at So if I'm doing +1 surgery, now the genus of the trefoil is 1. So 2g minus 1 is 1. So that means we are well within the range where this theorem is applicable. Okay? So let's look at, so n equals 1, s equals 0. So I'm just going to look at HF hat. Okay. So if I want to do the a, so a sub 0, a hat 0 is going to be that chain complex, right? Right? Okay, so there we go. That shows you, what do I have? I have 3 generators and a differential that hits from the middle one to the 2 outside ones, and so therefore the rank of the homology is 1. So this is all rank 1. Okay, and so therefore we see, so the Poincare homology sphere is an L space. Okay. Now, let's make one further observation. What about larger n? Okay. So, for larger values of n, okay, what could these a hat complexes look like? Okay. So, if I were interested in like n bigger than 1, s equals. So if s is bigger than 1, okay, let's just see, let's work out, maybe I'll do one of these over here. Okay, so this is the s bigger than 0, okay, and then bigger than 1. Okay, so I'm going to draw my chain complex. Okay. What do those hook complexes look like? Well, I go up to height s, okay, which might be here and it might be, you know, wherever it is. Okay, but you see that everything is supported between height values -1 and 1 on the x-axis, or sorry, on the y-axis, the j-axis. Right? So immediately I see that the homology of a sub n of a sub s is just isomorphic to f, right? There's just one generator. See, I see my 3 generators and a differential from one to the other, right? That's what the complex looks like for the s equals the positive s versions. Now, what about the negative s versions? Okay. Well, let's just take s equals -1, for instance. What am I seeing now? I'm just seeing a row, right? And if I take any s equals, if I shift s down to -2, I'll be seeing this row of the diagram. If I shift s down to -3, I'll be seeing this row, okay? Okay, so that tells me that, again, H star, the homology of a hat S, is again F, because there's only that differential, right? So what am I going to conclude now? So that tells me that n surgery on the right-handed trefoil is an L space for all n greater than or equal to 1. Okay? Hold on to that thought. Okay. So now I want to try. Let's try one more example. I think doing examples of this is often more instructive than stating a lot of abstract theorems. Okay, let's try the left-handed trefoil. Okay, so I didn't do the, so that was the Heegaard diagram for the right-handed trefoil up there. Okay, if I wanted to do the left-handed trefoil, either I could interchange the roles of red and blue, or I could reflect that whole diagram across either axis. There are a lot of symmetries going on here. Okay, so it's going to turn out that if you want to mirror a knot, to mirror a knot, just reverse all the arrows in this diagram. So CFK infinity of K mirror is going to be reverse all arrows, excuse me, and rotate by 180 degrees. Okay, so stand on your head. Okay, so let's take a look at that complex. Okay, so now this is going to be the left-handed trefoil. That's what the complex of the left-handed trefoil is going to look like. Okay. Mnemonic that I learned, that I figured out at some point when I was trying to remember which one of those two chain complexes gives me the right-handed trefoil and which one gives me the left-handed trefoil, is that this is an L. Okay, so now let's quickly look at what happens if I try to do large surgeries on the left-handed trefoil. Okay, so I'm going to look at the A hat 0 complex. Okay. Now, there are 3 generators in it, this one, and this one, but now suddenly there's no differential. Okay? So, what we're going to, right, because the differentials are all sort of here and here, there's no differential from here to there or here to there. Okay? So what I now see is that the homology of A hat 0 has rank 3. Okay? And immediately, what I can deduce from that is that, so this A hat 0 is going to occur as one of the spin C structures. If I do any positive surgery on the right-handed trefoil, then A hat 0 is going to occur as one of the spin C structures, namely the one that corresponds to S equals 0 under that identification. Okay, so what we're going to deduce is that the end surgery on the left-hand trefoil is not an L space for any n greater than 0. Okay, so now we're seeing, a great deal of information about when, so when do we have L space versus non-L spaces? Okay. So now, maybe let's even state something. Okay. Okay, so here's maybe a nice theorem. Okay, so let's just see what went wrong here. When we had this sort of lower left-hand corner in the complex, right, where I had an upper right, I had a lot of upper right-hand corners as I drew the complex. Here I was seeing lower left-hand corners, and lower left-hand corners somehow behave very badly with respect to these upper right-handed hooks. Right? They produce homology. That's what happens. Okay? So, theorem of Lorentz-Savo, is that if K has a positive L-space surgery, and for now I'm just going to say integral, although actually if it has rational surgeries, then we'll see. We'll be able to extend this to rational surgeries in a moment. Then CFK infinity of S3K, and this is specific to knots in the 3-sphere, okay? Well, it looks like the following. Okay, so that is to say, we're going to call this a staircase complex. Okay, namely, there are some collection of generators in, maybe I'll call it like A0, A1, A2, A3, blah blah blah. Okay, going up to some point, some degree, and the differentials of A1s are going to be the differentials of the odds are going to be the sum of the two consecutive evens, and that's it. Okay, now these arrows might have length greater than 1, okay, in this chain complex, right? So this is as I'm drawing it on the sort of IJ plane, okay, these arrows can have varying lengths, okay? So I might have, and then of course this pattern, this is the repeated pattern, right? As I take the the U action, just shifting I and J by 1, this pattern repeats, okay? But the point is that somehow that's it. Those are the only possible, that is the structure of CFK infinity, okay? Let's see.
Why need to restrict to S3 here?
Why do I restrict to S3? Well, I don't really need to restrict to S3. I just need to restrict to a homology sphere L space. Okay. So So this is the structure of the CFK. And what we call this is called an L space knot. So a positive L space knot. Usually L space knot means having a positive surgery that's an L space. Okay. Now, one corollary to this you can see. Let's notice that if I take this pattern, right, and I translate it, I take the translates of this thing, okay. Remember the vertical complex here, the complex that was on the line, on the y-axis, is just CF hat of the 3 manifold, okay, filtered by the Alexander grading, right? We said J minus I was equal to the Alexander grading, okay. So now, when I translate this diagonally, take all of those translates, and look at where each of these points lands on the y-axis, okay, then I'm going to get I'm going to get no more than 1 point, than one generator at each possible height on the y-axis, right? That's what happens when I do this translation. And as a corollary to that, what we see is that for one thing, the rank of HFK hat of S3K in any individual Alexander grading, okay, is equal to either 0 or 1, right? Either there is a generator or there isn't a generator in that slot as I translate everything. And as a corollary to that, we see that the coefficients of the Alexander polynomial of T are all 0 or plus or minus 1. Okay, so that means that in order to have an L-space surgery, for instance, the old question that people are still interested in is what knots can have lens-space surgeries? What knots in the 3 sphere can have lens-space surgeries? This, as far as I know, gave the first restrictions, even just on the classical Alexander polynomial of knots admitting such surgeries. Okay, so this was like an early use of these. Okay. Any questions about this formula?
In the first corollary, the subscript is an M or a star?
In the first corollary, oh, star. That's a star. Yes. Okay. All right. So now this was the large N surgery formula. Okay, and there is also a formula for dealing with arbitrary N, and I want to talk about it, but I want to come back. I want to come back to it because I realized that I forgot to talk about sort of one of the most important tools in our toolkit, which is the exact triangle for computations. And I want to make sure that I hit that before the end of the session. So we will come back later, maybe not either tomorrow morning or on Thursday, to be decided, to the integer surgery formula. But I want to make sure that we talk sufficiently about the exact triangle. Okay, so let's notice this pattern. So either we had like L space for all positive n integers, or L space for no negative n integers. By the way, of course, with the left-handed trefoil, the negative n surgeries are going to be L spaces, right? For the same reason. Well, one thing is that I guess I didn't say this explicitly, but Heegaard Floer homology dualizes under orientation reversal. Okay, so that's just a simple algebraic consequence. Okay, let's talk about the exact triangle. So let's try to state this in the most general way. So let's now let M be a manifold. It's going to be a 3 manifold with torus boundary. Okay, that's right. I'm under 35, so my closed 3 manifolds are called Y. So my open 3 manifolds, or my manifolds with boundary, will be called M. So we'll what I want to do is choose 3 slopes on this boundary. So sigma 0, sigma 1, and sigma 2 are going to be slopes. That is to say, simple closed curves on the boundary. On the boundary of M. And what I want to do, so they should be oriented, or I should oriented simple closed curves with the property that the intersection number, the algebraic intersection number of each one with the following one, where I take the indices mod 3, should be equal to -1. Okay? So what, for instance, might be instances of this? Oh, so -1. So this is going to be with respect to the boundary orientation. Okay, so for instance, what might some examples of this be? Let's suppose that okay, y minus the neighborhood of k. So let's let sigma 0 be the meridian. Okay, let's see if we can sort out the orientation conventions. So if I'm just thinking about the complement of a knot in S3, for instance, if this is the meridian, let's say the knot was oriented that way. Okay, so if K was oriented this way, and I want a right-handed meridian that goes like that. Okay, and then this was a longitude. Okay, this is the meridian. This is a longitude. Okay. Now, the intersection number of the meridian and the longitude, should this be 1 or should it be -1? Is -1, but okay, I guess with this convention I need it to be 1. Okay, so I want to orient this as the boundary of the three manifolds, so the outside. So with that orientation, red dot blue is 1. Okay.
How do you choose the meridian?
Oops, I chose it. Yeah, no, you're right. It was -1, so it should have been a right-handed meridian. That's right. Okay. Yeah. So I thought I had it right. Okay. Yes. So with this orientation, the red curve dotted intersect the blue curve is -1 when we orient this as the boundary of the outside. Okay. So I could take sigma 0 to be meridian, sigma 1 to be the longitude, and then sigma 2 to be the longitude plus the meridian. Okay. And I think if you check, that's going to be form. These will have this property. Okay. And let's let y sub I be the Dane filling of M, be M sigma I. So that's going to be, I'm going to fill in those 3 curves. So I'm going to have 3 different 3 manifolds. And if that's the case, we say that y0, y1, y2 form a triad. Okay. So for instance, this is going to be like y. If I have a 3 manifold and a knot, this might be y. This might be y sub n of k, and this might be y sub n plus 1 of k. Okay, that might be one way of doing this. But of course, I could also permute the roles of these things, and then this might relate different rational surgeries to each other as well. Okay, and that's going to be a very important notion. Okay, and a key theorem here, and actually one of the most important computational tools for any of these Floer homology theories is. This is theorem of Szabo and various generalizations. It's fundamentally theirs and has been stated in more general ways by various people, which is that if y0, y1, and y2 are a triad, then there are exact sequences. There are exact sequences relating HF hat of y1 y0, y1, and y2. And similarly, exact sequences relating HF plus of y0, HF plus of y1, and HF plus of y2, in which these maps are the maps induced by the 2 Hadal cobordisms. So, in which the maps are induced by 2 Hadal cobordisms. So I guess I didn't really spend any time talking about how one defines maps on the Heegaard Floer homology groups associated to a four-manifold, to four-dimensional cobordism. But the point is that when I have this condition, the intersection number 1 condition, you see that I can obtain, y1 from y0 by doing surgery by doing integral surgery along a knot, and doing integral surgery along a knot is the same thing as attaching a four-dimensional two-handle. Okay, and those induce these maps. Okay, so now let's think about what happens when so many possible things can happen if we try to think about the first Betti numbers. One possibility is that the first Betti number can change. Okay, that is to say, if one of those surgeries that I was doing was zero surgery along a knot, right? For instance, right? Remember I said yn and yn plus 1. Okay, I could be doing zero surgery and 1 surgery along a knot, and in that case, one of the 3 manifolds will have first Betti number bigger than the other 2. Okay. Let's not focus on that situation. Let's stick with the other possible situation of the case where they all have the first Betti number 0. Okay, so that's going to correspond, for instance, to start with a knot in S3 or a knot in a homology sphere, do n surgery, and do n plus 1 surgery, where n and n plus 1 are both not equal to 0. Okay, so if B1 of if all of these are rational homology spheres, okay, then it turns out that if you do a little bit of fiddling with homology computations, then up to reordering,
Integer or rational?
Rational homology spheres, yes, sorry, that's what I meant. If these are all rational homology spheres, then up to reordering, so those, the first homology groups are all finite, okay? And one of them is equal to the sum of the other 2 in rank, okay? So, or not in rank, in order. So the determinant of, let's say, y1 is equal to the determinant of y0 plus the determinant of y2, for instance. Okay, so that's just going to be some basic algebra that you have to do to figure this out. Okay, and now let's make the following observation. If so, if y0 and y2 are both L spaces, then so is y1. Okay, so why is this true? Well, let's just think about it for a second. So if I look at hf hat of y0 mapping to hf hat of y1 mapping to hf hat of y2, and then there's this connecting map that goes around. Okay, well this has rank, maybe I should call this, maybe let's call these determinants, I don't know, M1, M0, and M2. So this we know has rank equal to M0. This has rank equal to M2. Okay, and this has rank greater than or equal to M0 plus M2, right? Just because those are how the determinants are. On the other hand, if this connecting homomorphism were non-zero, then this would have to have smaller rank. Okay, just by doing this is the triangle inequality. Okay, so immediately we deduce that this has to be have the same rank as those other 2. Okay, so what we see is that when I have when two of the three are L spaces in this particular way, then the third one is as well. Okay. So a corollary to this, which could be stated, or maybe let's really state this. We can index things more precisely, and this is really, I guess, a theorem of Rasmussen and Rasmussen, is that if M has at least two L-space fillings, it has infinitely many. Right? And it's more than that. We can parameterize the fillings by the extended rationals. Okay, that is, say, the rationals union infinity, or if you like, QP1, the projective rational line. And the statement is that the L spaces form an interval. Either if there are multiple ones, then they form an interval within that line. So we'll come back and say more about this and how this fits in with the results that I mentioned previously. But now we see that there are like a lot of L spaces out there. So, okay, I think I'm out of time.
Another coffee break. I think we should try to start at 11:30 sharp.
Okay.